My name is Robertson. I am Group 43, and for my final project, I chose to do a comparison of several popular machine learning architectures for sentiment analysis. This process involved programming several of these architectures, training them, and then deploying the most successful of these architectures into an app that allows you to perform sentiment analysis of a song of your choice. My motivation for this problem is that I'm working on a project in the thesis program right now that involves music information retrieval, and I've been looking for a way to perform sentiment analysis on song lyrics, so I thought this would be an excellent opportunity to research some of the best ways to do this and perhaps create my own machine learning model that can do this efficiently. To do this, I began with the Kaggle dataset 500K Spotify songs with lyrics, emotions, and more. It was important that the dataset specifically contains song lyrics and emotions, as we need targets to train our models on. This dataset was a little bit difficult to work with as it was very large and the different classes of emotions were very unbalanced. As you can see in this table here, we have some classes with a lot of entries like joy, sadness, and anger, and some with very few like surprise and angry. For this project, I decided to focus on the top 3 emotions, joy, sadness, and anger. From there, we still had a problem of the dataset being so large that the model took way too long to train. So I reduced each of these classes down to 5,000 entries each. Once I had selected the dataset to work with, next I had to select which architectures I wanted to focus on. The most popular architectures for sentiment analysis are residual neural networks, long short-term memory networks, and transformer-based models. So those are my focuses for this project. Beginning with a simple residual neural network, we have worked with similar models in assignments in class before, so I expected this one to perform quite poorly, and it did perform quite poorly. But I felt it was still good to include this model as a sort of baseline going forward. Next up is long short-term memory networks, which were the focus of my project. A lot of time was spent fine-tuning parameters of this model. Starting with the basic long short-term memory model we used in class, I introduced much larger embedding and hidden layers. I also increased the number of epochs greatly and introduced dropout to help reduce overfitting, which was something that kept happening during the training of my models. I also introduced more complicated weighting and biasing of nodes and a sequential module chain. Another key difference between this LSTM model and the base LSTM model is that this one is bidirectional. The hope was that using a bidirectional model would help the model capture more context than a simple one-directional model. Context is very important in natural language processing, particularly in song lyrics and other forms of art. Context can greatly change the meaning of a word, so I wanted to test a bidirectional model against a single-directional model. In the graph on this slide, we can see a comparison between my custom-tuned LSTM model and the base LSTM we used in class. As you can see, the custom LSTM model has a higher accuracy sooner, but with more epochs, eventually the basic model overtakes the custom model. Next, and finally, transformer-based models. For transformer-based models, I chose to use BERT, a pre-trained transformer-based model. This model is specifically trained to be used in natural language processing, so it should be a perfect fit for this task. I felt using such a robust pre-trained model would be good to compare my models against. Unfortunately, due to the limitations of Google Colab, I was unable to run very many epochs of this model as the runtime kept crashing due to running out of RAM. Even from the minimal amount of epochs we can run, we can see that BERT has a high level of accuracy early on, though our models do reach that level of accuracy once we've completed more epochs. Next is the final stage of the project, deployment. For this, I've created a basic demo of an application that could utilize the networks I've trained. This app presents the user with a basic front end developed using PyQt PySide 6. Through this GUI, you can search for a track and artist. Using this track and artist combination, the app will get song lyrics from the Lyrics Genius API, and will classify these lyrics into one of the 3 classes that we trained our models to classify text into. Specifically, I'm using the custom LSTM model that I developed for this project. Here's a video demonstration of the application running. Here we can see you load the application through torchapp.py, type in an artist name and a track name. We're starting here with a happy song. You can then see the application working in the terminal here. It's found the song on the Lyrics Genius API, and it is now classifying the text using the custom LSTM model that we discussed earlier. And as you can see, the results are displayed at the bottom there, with the model saying that this song is 94% likely to be a happy song. Next, we're going to search for a sad song. And here we can say the model says that this song is 99% likely to be a sad song. Since an important part of this project was discussing deploying these models into applications and systems, I wanted to discuss some next steps that could be taken if this model were to be deployed into a fully featured application. Firstly, these models are very slow to train due to requiring large embedding and hidden layers and a large amount of epochs to reach satisfactory accuracy. I believe that with more time, a sweet spot of parameters could be found that could be the perfect balance between large layers that allow for high accuracy and smaller layers that allow for fast training. Faster training means we could use many different models depending on the situation, as certain models can be better suited to different types of song lyrics. Next, I would want to address issues with the transformer models. As mentioned earlier, when using BERT models, Google Colab kept crashing due to running out of RAM. This model showed high levels of accuracy in the limited tests we were able to run, and with more dev time, we would be able to create our own transformer-based model that could find a balance between accuracy and computational cost. Finally, I think it would be ideal to include more emotions than the 3 that we used in this project. Specifically, many datasets and models use Russell's model, as we can see on this slide here. Russell's model has 4 main quadrants, being happy, angry, sad, and relaxed, but also has many subcategories in these quadrants to represent more complex emotions. As songs are often meant to represent complex emotions that aren't just angry or happy, a more complicated emotional model like this would be incredibly valuable in lyric sentiment analysis. The difficulty would be in finding a dataset that equally represents all of these emotions. As we ran into earlier, many datasets either have few emotions represented or, in the dataset we used in this project, have many emotions represented, but lacking in data points for certain emotions. A workaround for this would be to use the models we trained for this project to create our own dataset. Expanding these models to account for more emotions than the ones we used in the project, we could find datasets that do not include emotions and add emotions onto them. This would greatly increase the number of datasets available to us. Combining this with the use of the Genius Lyrics API as we used earlier, we could create our own datasets from scratch of lyrics classified by emotions. And that's it for my CSCI 4050U final project. Thank you for watching, and I hope you enjoyed the presentation.